Hello, my name is Schuyler Trenary, and on behalf of Team 8, I am proud to present you with our findings for Phase 1 of the design project. In Phase 1, the team was tasked with creating a high-altitude, long-endurance aircraft that could be used for research, communication, and surveillance by multiple users. The aircraft design required modular payloads that could be switched out quickly. 3 potential designs were created, but only the best design was chosen to run the calculations on for the location of center of gravity and propulsion estimates. For this phase, the team needed to provide the structural layout of the aircraft, as well as possible materials for building the aircraft. Finally, every decision made on design choices and the approach used had to be justified through a down-select method. The design of this aircraft was primarily driven by the requirement that the aircraft make it to the station that is 1,000 nautical miles away at an altitude of 55,000 feet in under 3.5 hours. Once at the station, it must loiter for 16 hours before it flies back to the base, while maintaining IFR fuel reserves. Another big driver for the design was complying with military and civil standards for airworthiness certification. In order for the aircraft to even be considered, it must be certified, which means the following the regulations in Military Handbook 516 and CFR 14 Part 25. The final major design driver is being able to use a runway that is 9,000 feet long for both takeoff and landing at max weight, and doing this in possible icy conditions.
Our team considered 3 potential designs. The first design looks very much like a commercial jet you might see flying in and out of an airport. It has an elliptical fuselage with tapered wings that are slightly swept back. This design has the advantage of decreased drag at higher speeds because of the swept wings. The disadvantage is the swept wing has poor directional stability at high speeds, and the wing has a tendency to stall at lower speeds. Our second design has rectangular wings and a conventional tail. The rectangular wing planform has the benefit of producing the most lift out of any planform at low speeds, and the benefit of being simple to produce, which will reduce the manufacturing costs. A disadvantage of this design occurs when the plane is reaching higher speeds near Mach 1, where it becomes less efficient. The third design has a similar fuselage to design 2, but it has a delta wing planform and a V-tail. A delta wing is efficient at supersonic flight, but the low aspect ratio provides less lift. Our team has decided to proceed with design 2. A few of the key factors that contributed to the down-select process in the selection of design 2 were having the ability to do an accurate analysis of the aircraft and in an effort to conform with the Code of Federal Regulations for transport category aircraft. In order to meet both of these criteria, a more conventional aircraft design was chosen. By going with the traditional design, our team will have an ability to better analyze our design and be more confident in the results that we find. The other point to make is that an aircraft design will only ever be a design unless it is able to get the proper certifications to fly. As a team, we think our best chance at meeting the certification requirements will be through a more trusted and traditional design. Now on to stability and control. Like most planes, this aircraft will need to be both statically and dynamically stable. Similar to one of our benchmark aircraft, the Global Hawk, we will not use secondary control surfaces like flaps or slats, and the control surfaces can be moderately sized because we will have little need for tight maneuvering. We believe this simple control surface design will help us conform to regulatory standards. As you can see here, the design is a traditional wing and tail configuration. We will want to keep our tail volume ratios within these ranges for well-behaved flight. Because of our design, we will want to have a center of gravity that is near the quarter core of the wing, which is about 44 feet from the nose of the aircraft. Based on the calculations, this plane will have a CG that is 45.7 feet with no payload and a CG that is 44.4 feet with full payload. Even with other payload configurations, we can stay within 5% of optimum CG, making this a stable and robust design.
Shown here are the propulsion characteristics of our aircraft. The main takeaways from this information are the numbers you can see listed here. As you can see, we have decided to go with 2 high bypass turbofans. This was decided after analyzing benchmark planes and considering the efficiencies associated with high bypass. Each engine will need a minimum uninstalled thrust of 31,000 pounds to facilitate takeoff at max weight. We have also considered the redundancy of using 2 engines with different mission profiles. Because of the weight of this aircraft, the propulsion system will be of extreme importance for getting off the ground and being able to loiter for extended periods of time.
Team 8 chose a standard aircraft structural design consisting of ribs and spars in the 150 feet long wing with a mean aerodynamic chord of 15 feet. The fuselage, consisting of longerons and frames, is 100 feet long, made from aerospace aluminum, specifically aluminum 7075-T6. Aluminum is readily available and easy to manufacture since it does not require a lot of special machinery to process. The payloads were placed in the aircraft with the zenith payload in the fore and the nadir payload in the aft. The side viewing payloads are placed in the fore with the zenith to allow for minimal viewing obstruction. The radome was placed in the nose, while the remaining volume is partitioned to the system electronics. The rationale for this design from a structure's point of view is that the wing is easy to analyze with no sweep or taper, and the fuselage is a series of elliptical cylinders, making them easy to analyze as well. There are some potential issues with the chosen design, mainly how heavy the aircraft will be if it is solely made out of aluminum. At this weight, it may be difficult for the aircraft to make it to the station in under 3.5 hours and have enough fuel to complete the mission. A possible solution to this is to make the aircraft lighter by using alternative materials along with aluminum to shed weight. Another problem is that the aircraft will need a thrusty engine to make it to the station altitude in the appropriate amount of time, which again brings up running out of fuel before the mission is over. This could be remedied by choosing a more fuel-efficient engine, but fuel efficiency and fast engines usually do not go hand in hand. This could mean the aircraft will need to be refueled while in the air in order for it to make it back to base after its 16-hour mission. This mission will be very challenging since there has never been any unmanned aircraft that has had a payload this heavy and flying at an altitude this high. There are few comparable aircraft for the team to use to benchmark information from. In addition to that, there are potential issues meeting the on-station time and altitude in the 3.5 hours while maintaining enough fuel for the return trip. These issues can be resolved by choosing the right engine and material for the aircraft in order to meet requirements.